Good evening. Now we will continue with our lectures on ship propulsion. Please pay attention. We'll continue. This is ship propulsion number 2. Thank you. Okay, as it is, last time we talked on ship propulsion, and we mentioned that the ship resistance is the beginning to determine the power the ship requires. And then we mentioned that the ship resistance is comprises of frictional resistance. This is the higher level, the higher quantity. Then and depends on the surface area of the immersed portion of the ship. Then after that, we have the wave making resistance and the eddies making resistance. These two comprise of what we call residual resistance. Then we have the air resistance also. So we mentioned all this in our last lecture. We also mentioned appendages resistance. Okay, there are other types of resistance which also comes apart from this appendages resistance. There are others. So I will show you other resistances that the ship has to have to withstand. So we have the steering. When the ship steers from one direction to another direction, so this induces more resistance. Also, we have others like the wind. When the wind is blowing against the ship, that is additional resistance. When also the current, the ocean current, is coming against the ship, is also added resistance. But when the current is behind the ship, pushing the ship forward, the resistance will reduce, or either the current or the wind. And that's the adage when we give you good wind. That means the wind is coming from astern. Then it will reduce the resistance. It will give more power to reduce the resistance of the ship. So we have added resistance due to waves. When the waves are coming, they lead to more because there is motions. The ship has 6 degrees of motion, pitching, rolling, all these motions in different directions take energy and increase the resistance of the ship. It has 6 degrees, surging, rolling, pitching, heaving, swaying, yawing. Okay, now we'll see that later, but now we're talking of resistance. So all these motions increase resistance. So we have the increase in resistance when there is a restriction in the channel where the ship is moving, like when the ship is coming through a small channel, and the waves that are going out are reflected back. And when the waves are steeper, and bigger waves means more resistance. Also, the bottom of when the distance between the bottom of the ship and the depth of the water is shallow, also this leads to what we call squatting, and this increases the resistance of the ship. Now, these are other resistances. We also have a ship that is kept in one place and is not used for some time. There are some marine growths that grow around that ship, shells, mollusks, and all these weeds that grow on the ship body. This also, especially in this tropical area, this increase the resistance of the ship. So the ship needs to be cleaned up in order to reduce because all these things will reduce the speed of motion of the vessel because of the increased resistance. Okay, so now having seen all this, the person that actually came to visualize all these things and try to quantify the resistance of the vessel, somebody did it, and that is the person in the name of Freud. Sigmund Freud did that. He now said, how do we quantify all these resistances? How do we quantify it? So he decided to divide the resistances into two. As you can see here, he said resistance comprises of total resistance, residual resistance, and frictional resistance. The frictional resistance already we know. The residual resistance, as I told you before, comprises of the eddy making resistance and the wave making resistance. The other resistances are not quantified in the calculation of resistance of the bare hull. We're talking of resistance of the bare hull. But when we are calculating the resistance of the ship, all the resistances should be accounted for. Normally, the air resistance is the body, is the part of the ship that lies above the water surface, constitutes what is from there we're having air resistance. That is also quantifiable. Okay, but then the others, all these other ones, like wave, due to wave and the wind, and all these appendages and others, they are all they can put some percentage. After calculating the bare hull resistance, we add a percentage, normally about 15%, to take account of all those ones, because they are the ones we cannot easily quantify. Okay, now when we want to quantify now, we want to get the frictional resistance and the wave making and the residual resistance. The frictional resistance, okay, the frictional resistance, how do we get it? This is the method that Freud adopted. He now talked of using this tank. This is what we call towing tank. Towing tank is a long tank shaped in that manner, as you see in the drawing. And then inside this we pour water and we put some wave damping so as to minimize the waves coming due to wall effect of the channel. So we now put a model, a ship model inside, and tow it, as you can see, on a railroad arrangement that has a carriage. The carriage has a motor that drives it to different speeds, and as it's driven to a uniform one single speed at a time. And then it has a dynamometer or instrument to measure the towing force with which it is towed at a particular speed. The towing force of the model will show, and this is what is the total towing force. That's the resistance of that model in the water. Okay, now when we get the resistance of the model, Freud now proposed some methods, as you can see here. You can see he proposed some methods. Look at it. First, he said, to determine the total resistance, you measure the total resistance of the model. What this model is made to be geometrically similar to the ship. What do we mean by geometrical similarity? It means that the ratio of the length to breadth for the model is the same as that of the ship itself. The ratio of the length of the ship to the length of the model is constant, and it's the same constant is the breadth of the ship to the breadth of the model, the same constant. The depth of the model and the depth of the ship and over the depth of the model. So they are in a constant ratio. And then not only that, their block coefficients are also the same. All the form coefficients are the same. So we can now say that the ship and the model, they are geometrically similar. Then after that, you estimate the frictional. How do we get the frictional resistance? We get the frictional resistance of this model by calculating the surface area of that model. Now, this surface area, if you get a plank of the same surface area as that model and throw it inside the water where it does not make any waves, it's totally submerged, then you can get what is the frictional force that is required to tow a surface area equal to that model. So, this was the method that was used to quantify the frictional model, or frictional resistance. Okay, now we are still moving. As you can see, we have to determine the value of residual resistance. That is the residual resistance of the model can be calculated when we have the total resistance minus the frictional resistance. Every other thing there is the residual resistance of the model. And now we use Freud law of comparison. There is a law which is written here that the resistance of the ship is equal to the resistance of the small model times the cubic power of the ratio of lengths of the ship against the length of the model. This is the formula that gives us the residual resistance of the main ship. Then how do we get the frictional resistance of the ship itself? You see, we can determine the frictional resistance of the ship using the same method. So there is a formula. Look at this formula. This formula here. You see, R equals to FSV 1.82. This is how to calculate the frictional resistance. Frictional resistance depends on the surface area and that factor F. This is the factor F is determined by experiment, using flat sheets, plywood sheets, and of different area. And the table is prepared. Like you can see the table here. This is the table. This table, you can see. In this table, it is given the length of the shape and the value of F against the length of the shape. You see? So with it from there, we can get the length of the model or the length of the shape, as the case may be. So you can see it is ranging up to 350 lengths. So you see that it covers the length of so many shapes that can come into. So once we calculate the frictional resistance of the ship plus the residual resistance, then we can now get the total resistance of the ship, as you can see here, going by this equation. So that is how we can quantify and get the total resistance of the ship. And this is where we stop today. You have learned today how to quantify the frictional resistance, the residual resistance, and the total resistance of the ship, based on the law of comparison, fluid law of comparison. We can be able to get this fluid law. We will talk more about it. It is from hydrodynamics that it came to be. So, and that is how it is to quantify this. Thank you very much. We'll have you in the next lecture.